Welcome back to Machine Learning class. After the welcome session and two Python review sessions, we're finally going to learn the first machine learning algorithm, linear regression. Today, we're going to cover the concepts, techniques, and intuitions associated with linear regression. Next time, we'll have hands-on work. Now let's just first step back, think about how humans learn. One way for humans to learn is to learn from mistakes. When we make a mistake, it often comes with a cost. In the cartoon, the boy's hand is burned as he is trying to hold the handle of a burning pot. Next time, he likely learned from his mistake and will be able to avoid being burned again. Another way for humans to learn is to recognize patterns so that we understand the differences and similarities among things around us, then make proper decisions accordingly. In either way, learn from mistakes or recognize patterns, we often do not learn right away. Instead, we learn through trial and error. During the process, we optimize our behavior. Machine learning algorithms can learn in similar fashions by relying on statistics. In machine learning, if we can establish a cost matrix and find a way to keep reducing the cost, then the machine learning algorithm is going to get better and better iteratively. In a sense, it learns by itself. In reality, the opposite side of cost is reward. So a machine learning algorithm could also improve itself repeatedly by maximizing reward. A machine learning algorithm can also identify the differences and the similarities among observations and then make decisions accordingly. Now let's look at a very simple linear regression example. Here we have 6 observations and we have x variable and a y variable. If we plot the 6 pairs of x and y on the chart, it looks like visually a straight line can do the job. So that's why linear regression could be a proper method for this particular example. But now the question is, which line is the best line? Should it be steeper or flatter? And what's our criteria? Well, one criterion of determining which line is the best is to ensure the line does not have a bias. Looking at this line be proposed here, we can tell this line has a bias because everywhere on the chart, this line is always above the actual observations vertically. So there's an overprojection by this particular line. Either overprojection or another line which is below, kind of underprojection, is bad because those kind of lines that overprojection happens or underprojection happens is a biased line. So that's why it's not good. How about this line? Well, it's still not that good because another criterion of determining which line is the best to ensure the overall projection error is the minimum. Looking at this line here, we can sense that if we anchor the line here and just rotate the line little bit clockwise, we can imagine a new line probably can make the predictions better, means the new line's prediction are closer to actuals. So that's why this line is not the best either, because it's not producing the minimal prediction errors. How about this line? This line looks pretty good. Actually, this is the best estimation for the particular example with linear regression. And for this line, mathematically, it can be written as y equal to 1.9114 times x plus 26.933. So how we can conclude this line is the best? Let's do a few things. If we just use this equation to make predictions, and we're going to get y prime, which means prediction from our linear regression. Then we calculate the error, which is defined as the difference between actual y values and the model predicted y values. This each number here is simply the difference between the prediction, the difference between the actual and the prediction. Then we do the squares of the prediction error, and we get to this yellow highlighted column, which simply is the square of the error, observation by observation. In the end, we can sum up all the squares of errors, or even divide it by the number of counts, which is 6 here. So the criteria of the best prediction is the one which can produce the sum of squares, or equivalently, the sum of squares of errors divided by count, because the count is fixed. Those two are equivalent. You can minimize either one, which will give you the equivalent outcome. So the basic idea is a machine learning algorithm will also need to define a cost. In linear regression, the cost is defined as the sum of squares of errors. And whenever you have a way to minimize the errors, minimize the cost, this linear regression estimation is the best. Basically, the linear regression estimation's job is to come up with the slope and intercept, which can produce the minimum cost. Whenever that goal is achieved, we claim this linear regression estimation is the best. Here to summarize, if we have only one independent variable like this, x1, this linear regression can be written as this form: y prime, the prediction, is equal to b0, the intercept, plus b1, the slope, times x1. Basically, there are two coefficients, also known as parameters, need to be estimated for this regression line. If we have multiple independent variables, also known as features, x1, x2, x3, all the way to xk, basically we need to have b0 again, which is the intercept, b1 is the slope for x1, and b2 slope for x2, b3 the slope for x3, then lastly bk the slope for xk. So now we have k plus 1 coefficients to estimate for this generalized multivariable linear regression. So now look at the chart. If we only have one variable, in the case k equal to 1, we can imagine and visualize the line in the two-dimensional chart, x and y. Basically, the best linear regression is the best line that can fit the observations. And when k is equal to 2, we have two independent variables and three parameters, b0, b1, b3, b2, sorry, also can be denoted as beta 0, beta 2, or beta 1, right? Those are just like equivalent, beta or b, they are equivalent. In this case, you can visualize that the best linear regression basically is to find the best plane that fit all the observations with minimal prediction errors or with the lowest cost. When k is greater than 2, means more than two variables, two independent variables, it's hard to visualize on the paper, but the math still works the same way. The goal is still to minimize the cost, so the corresponding coefficients with the minimum cost are the best estimation for a linear regression with multiple variables. Now, let's look at the summary again. Here, our notation is we have k independent variables, k1, k2, k3, all the way to x1, x2, x3, all the way to xk, and only one dependent variable, y. And if there are n sets of values of respective x1, x2, x3, all the way to xk and y, given there are n observations in data. So the job to determine the best linear regression is to find the best estimates of coefficients b0, b1, b2, b3, bk. Basically, there's k plus 1 parameters need to be determined. The prediction from such a linear regression model can be denoted as y prime. So we define the cost. The cost can be defined as the sum of squares divided by the count, or just the sum of squares of error. Again, those two are equivalent because given any given set of data, the n is a constant. Either you divide by n or not divided by n, your estimation for the coefficient should be equivalent. So how to determine the coefficients b0, b1, and to bk? There are probably at least two approaches. One approach is through analytical solution to derive the best estimates. What that means is you just plug in the corresponding x and y. A formula will give you the right answer for all the coefficients b1, b0, or b2, and right away with one shot. So that's called an analytical solution. We have the details in the appendix right here. So to make things brave, often x and y and beta or the coefficients errors are using the matrix notation. And with a linear regression in the matrix notation, the coefficient either b or beta can be derived using the transformation, multiplication, and inverse. Such operations of matrix and be derived analytically. So this is an analytical solution. Now let's go back. There's another approach which is more generalized. It's called gradient descent method, which we're going to look into more details. This method is another way to determine b0, b1, b2, all the way to bk. This approach is more like machine learning approach. Now let's first get some intuition about gradient descent. Imagine there's a little ant want to reach the bottom of a bowl. the ant starts at a random location right here. At this point, the ant has to make two decisions simultaneously. One decision is to either turn left or turn right, and same time going forward or backward. When the ants make such decisions, the goal is to get itself lower and lower. So with that, the ant make the first decision, which get it lower. Then at the new point, the ant is going to make the same decision, go left or go right, go forward or go backward. Anyway, the ant makes the right decision and it finds a path that help itself eventually get to the lowest point of the ball. So the intuition is here. Just as an ant want to climb on a surface, and the optimization, the goal is to find a path which will get itself to the lowest point. Well, now let's using our early linear regression example again. We know this regression can be expressed in the form of y prime equal to b0 plus b1 and x. So the goal is to find the best b0, b1, so that can yield the lowest prediction error. How to do that? We don't know anything. We can just pick random values to b0 and b1 to start with. With that, we make prediction. Then we measure the cost with the initial prediction. Then the next step is we can figure out a way to update the B0 and B1, which could reduce the prediction cost or the prediction errors. So it's just like ant, we have to make two decisions simultaneously. Either adjust B0 up or down, and at the same time, either adjust B1 up or down. The decisions actually can be made on the basis of partial derivatives of the cost function versus B0 and B1 respectively, and we have more details in the appendix. By keep adjusting the B0 and B1, the cost gets lower and lower. Eventually, the cost reached its minimum, and this time the B0 and B1 values are the best estimates of the linear regression, then the job is done. Something like this. We start with certain random B0 and B1, then along the path, the cost gets lower and lower, which is like ant climbing through a path, reach the bottom. In our case, the cost of the prediction is the minimum. So same idea, just like ants is climbing down through a path to reach the lowest point of a surface. In our case, the surface is a cost function with B0 and B1 as input. So if we jump to the appendix, and here just give some kind of more formal description of how to execute on the gradient descent procedure. Basically, it relies on the definition of partial derivatives. One thing worth mentioning is there's an alpha parameter or something looks like A here, which is learning rate, is the rate, the percentage or fraction applied to the partial derivatives when we update the coefficients step by step. Anyway, the idea of gradient descendant is like getting to the final answer step by step or iteratively. So we can have different view of the process of getting to the minimum cost. If we imagine if we have a knife or have a plane we can cut through, and we cut somewhere vertically, we can have intersection view. It's just like this, where the B1 is kind of fixed by B0. We cut kind of line where is from the intersection of the plane with the surface on this page. And on this line, when the B0 is updated and the cost is reducing gradually, eventually to the minimum value, the minimum cost. We could also have another view. Imagine we're a bird. We fly over the cost surface and we look down. Then this gives us the top-down view. In this view, you see the circles. The outer circles are the circle which is associated with higher cost. The inner circles are associated with lower cost. So the closer to the center, the smaller the cost is. The way you get there is gradually approaching the optimal B0, B1 estimates. So that's top-down view. The last view I want to share with you is the iteration step view, because we're not getting the final answer for the B0, B1 right away. We're getting there gradually. So as the number of trials and errors is increasing, most likely the cost will be decreasing. Eventually, you see the cost line may flattens out. That means we are reaching to the optimal point, and maybe that's the time we should stop. Anyway, we quickly talk about the gradient descendant and some intuitions, and also look at one particular example using the linear regression we just looked at earlier. But one thing to point out is the gradient descendant is a very generalized method. It works not only for linear regression, and it works for many other machine learning algorithms. So that's why we are spending more time looking to this approach, because we're going to use this approach again and again for our future machine learning algorithms. Finally, let's look at the comparison between two approaches, the analytical versus gradient descent approach. And we look at three criteria. First, does the method require trial and error? For analytical approach, the answer is no, because the formula, as long as you plug in the x and y, will give you the answer. There's no need for trial and error. So that's an advantage for analytical approach. And gradient descent, it requires trial and error. Second, can this approach handles huge number of features at ease? For the analytical approach, that's not the case, because as the number of features increase, or in our early notation, as the k increases to a very big number, so the analytical solution may take a lot of time and computing resource to compete, because the matrix inverse is a very expensive calculation. On the other hand, the gradient descent approach still can do things at ease, even when the number of features is huge, like the k is huge. So that becomes an advantage for the gradient descent on this second criteria. The third one is whether the approach is generic. Analytical solution is not generic. We have very elegant solution for linear regression, maybe for some other nonlinear case, but when the function form, when the algorithm gets more complicated, quite often there's no analytical solution. In that case, the gradient descent is the main approach we have to rely on. So by now, we pretty much concludes today's concept, techniques, and intuition part of the linear regression. See you all next time, and we're going to look at the actual data, do some actual work with the linear regression approach.